How do we bridge the gap between raw motion and precise data? Welcome to the project presentation for Group TYH2. Today, we are excited to share our journey in the design and development of a low-cost, air-cooled ECD for EV applications. Remember to enable subtitles before the video starts. Let's have a brief recap. An eddy current dynamometer is precision equipment used to examine the performance of a two-wheeler EV by measuring torque and power output through a controlled electromagnetic resistive load. This is the dynamometer that we built last semester. However, after our initial build last semester, we encountered critical hurdles. To address these, we have split our mechatronic solution into two vital domains, mechanical and electronic. In terms of mechanical, our primary villain was unrepeatable and unreliable torque readings. When electromagnetic resistance occurs, the backplate tends to resist it, causing the load cell to bend. This physical deformation is processed into the operating torque of the EV. The original design relied on the rigid C-beam stress plate to hold the backplate. However, this mounting was too stiff, causing mechanical binding during braking. This led to torque readings that were erratic and impossible to repeat. To solve this, our key innovation was changing the way we hold the backplate. We replaced the stationary stress plate with a custom-engineered bearing housing. This allows the backplate to pivot slightly on the shaft rather than being locked in a rigid, stressed position. This is the isometric and front view of the setup. Inside this housing, we utilize a high-performance dual-bearing setup. On the left, an NSK 6306 deep groove bearing with a limiting speed of 9,500 revolutions per minute. On the right, an SKF 7306 angular contact bearing with a basic dynamic load of 32.5 kN. As the roller assembly drives the shaft, the bearing on the left ensures smooth and concentric rotation. This deep groove bearing allows for the slight free spin needed for accuracy, whereas the bearing on the right handles the complex combined loads. This angular contact bearing ensures the assembly doesn't deflect or wobble under the stress of electromagnetic braking. This combination directly solves the mechanical binding issue. This is the top view and the side view of the dyno assembly upgraded with bearing housing. This is the CAD drawing of the bearing housing. And this is how all the components are assembled. Looking at our final CAD assembly and bill of materials, every component has a dedicated purpose. First outcome is decoupled load path. By utilizing a combination of an SKF 7306 angular contact bearing for axial thrust and an NSK 6306 deep groove bearing for radial support, we successfully decoupled the shaft's motion from the backplate's reaction. The most significant impact is the restoration of repeatability. Applying the same load now yields consistent torque data, solving the issue of system performance degradation. Mechanics was only half the battle. Electronically, the system lacked a real-time feedback system, leaving data vulnerable to human error and load fluctuations. To solve this, we developed a custom-built dynamometer controller. Inside the box, the Arduino Mega serves as the main controller, handling sensor inputs and PID control. XY3606 buck converter steps down the supply voltage to safely power the system. The LM2903 circuit conditions raw sensor pulses into clean digital signals for accurate RPM measurement. PC817 optocoupler provides electrical isolation between the control and power stages. D4184 MOSFET module acts as a high-speed switch, controlling current to the dynamometer called via PWM. At front panel, an LCD displays real-time values, while a rotary encoder allows the user to adjust the set point. This is how all the components are connected and integrated into a control system. So, how it works, the controller executes through three dynamic modes. The first mode is manual mode. This mode provides a direct output where the PWM duty cycle is proportional to the set point. The rotary encoder set point directly dictates the power sent to the dynamometer load coil. The next mode is speed control mode. It is a closed loop where a PID control algorithm adjusts the PWM duty cycle to keep the motor speed constant despite torque variations. The Arduino will measure actual RPM via the proximity sensor and compares it to the target set point. If engine speed is greater than set point, it will increase load, which PWM will be increased to speed up engine and vice versa. The last mode is torque control mode. It uses a PID loop to modulate PWM based on measured torque values. The Arduino will read the actual torque via the load cell and HX711 amplifier and comparing it against the target set point. If torque is smaller than set point, it increases PWM to pull engine harder and vice versa. The enclosure is fully 3D printed in high-strength ABS. Inside, the exploded view shows a structured layout. The final CAD drawing includes an exploded view and bill of materials. Our key innovation is the raised grid platform, which hides wiring beneath the platform. This made the internal structures neat, safe and simplifies maintenance. We also designed special vents for ventilation purposes. The outcome is closed-loop precision. With a PID control system, we can now maintain a steady state for both engine RPM and torque set points regardless of throttle fluctuations. Major impact is human error mitigation. Automation via speed and torque control modes significantly impacts data quality by removing the inconsistencies inherent in manual loading. Here is a simple demo video. We test it using an electric motor by focus applied. We throttle to a certain speed. The proximity sensor will measure the speed from receiving pulse, while the S-type load cell will measure the load and torque is calculated using formula. The LCD will display both the RPM and torque value in real time. In conclusion, by integrating a precision-engineered bearing housing and an intelligent Arduino-based PID controller, we successfully resolved unreliable torque readings and created a feedback control system. This low-cost, automated solution enables professional-grade performance mapping for electric vehicles, directly supporting global goals for innovation and sustainable transport. Thanks for watching. Remember to hit a like and share if you like this video.